Hey, welcome back. In this video, we're going to talk about the close friend of the ellipse, the hyperbola. As we've previously defined, the hyperbola is the set of points whose sum of the distances between two fixed foci is constant. Or in other words, if D1 and D2 represent the distance that one point is from the two different foci, those will add up to be a constant. And importantly, as we constructed the ellipse, it created this spherical type object that is in some way bounded around the two foci. The hyperbola has much the same setup. We're starting with two foci. We're going to analyze the distances. The difference here, you're going to see it has a radical change in the shape. The difference is that we're taking the difference of the distances that the point is from the two foci. And importantly, that difference is constant. And when we're looking at the distances, we're going to consider absolute values because we don't want to have to delineate which distance is larger than the other. So the only reason for the absolute values in this statement right here is because, well, whether you're closer to one foci or the other, one of those distances could be greater than the others. But importantly, unlike the ellipse, when we now go to construct the hyperbola, it's a radically different shaped figure. As we go away from one foci, we actually go a little bit away from the other foci to keep this difference constant. It is a big difference between these two constructions. Is since the summations add to be the same value, we're bounded and we kind of circle back on each other in this shape right here. But with the hyperbola, we end up having this asymptotic behavior as we extend away from the foci on both sides. So that's a quick introduction to the idea of a hyperbola based on the construction of its shape. But let's now, as we always will with these, look at the algebraic nature of hyperbola. All right, I want to start by just saying that I'm not going to spend the time showing the proof of these algebraic representations of hyperbola, but the basic textbook or online resources can show you that proof. We start with the definition of the hyperbola as being the difference between 2 points. We set it to a value equal to 2a. Do a bunch of algebraic manipulation, and we end up with these two statements right here. The important thing to understand about the equation of a hyperbola is, one, it's extremely similar to the creation of an ellipse or the equation for an ellipse. The main difference is that one of the two terms is negative and one of them's positive. So, unlike an ellipse, the equation for a hyperbola has one positive term and one negative term. And importantly here, unlike the ellipse, the values of these a squared and b squareds don't determine the major and minor axis. In fact, for hyperbola, there's only one axis that we talked about, the transverse axis, and that is not determined by the size of these values of a and b, but instead determined by the sign of the term. Specifically, in this case right here, since we have a positive x term, or positive x squared term more appropriately, the transverse axis in this case will lie along the x-axis. And then in the second representation here, where we have a positive y squared term and a negative x squared term, for in this case, for this hyperbola, the transverse axis will be on the y-axis. I'm now going to sketch the representations of both of these representations right here. Specifically, I want to attack this idea, what the heck does it mean to have a transverse axis on this axis or the other axis? And then once I have those graphical representations, I'll label all the important points that we're going to have, like the location of the foci, the vertices, and in the case of these hyperbola, the asymptotes. All right, so here we have a general sketch of both of these cases right here. And now hopefully it makes sense what I'm meaning by this idea of the transverse axis. In this case right here, for this hyperbola, which by the way, in pink here is the hyperbola. All the blue is just structural stuff used to create the hyperbola. But the transverse axis lying on the x-axis is this axis right here that runs along the x-axis that connects the vertices of these two shapes, these two parts of the hyperbola. And in the second case here, the transverse axis goes directly down the y-axis right here. And importantly to reiterate this as we move forward, when you're going to graph one of these hyperbola, the positive term determines the orientation. So in this case, since the positive term is the x squared term, the hyperbola shape appears oriented along the x-axis. And then conversely, if the y to y squared term is the one that's positive, our transverse axis lies on the y-axis, which means the hyperbola shape here appears oriented vertically. And importantly to note again, the a squared in this case is not determined like the ellipse as the larger of the two values from here, from the a squared and the b squared. The a squared is solely the one connected to the positive term. All right, so now we have a sketch. Given our general form of the hyperbola, let's go through and label the important pieces. First and foremost, we have the vertices. The vertices are here along the transverse axis. They look a lot like the vertices of a parabola, but in this case, when we're oriented along the x-axis right here, we're going to have one vertex at a comma 0 and a second vertex here at negative a comma 0. Also, not part of our graphical representation, but defining part of the construction and important in the applications of hyperbola are the foci that we talked about in the beginning of this example, the beginning of the video, to describe the construction of the hyperbola. The foci are located at c comma 0 and negative c comma 0. Importantly, in this case, c squared equals a squared plus b squared, and that's true in both cases. And then finally, a very important part of the construction of a hyperbola is its asymptotic nature. And here you've seen I've sketched in these two slant asymptotes. These are fairly easy to find. This first one right here is y equals b over ax. And I'll talk more about this in a second, but I've constructed this rectangle here. I'm always going to do this when I create these hyperbola. The reason I create these is they give me a location for my vertex that lands right here, but then also the box through the corners, I can easily construct these asymptotes. But importantly, as you'll see this line right here, and this definition should make sense as far as a rise over run of this box I've represented here, but we have one slant asymptote at y equals b over ax. That's this asymptote right here. And we have a second asymptote at y equals negative b over ax. All right, at this point, it might seem like there's a lot going on. You've just been introduced to this conic section, and visually this can be really overwhelming, but I want to bring it back just a little bit before we get to the vertically oriented hyperbola, is that there's three main players, really two of which you care about when constructing these. We have the vertices, we have the foci, and we have the slant asymptotes. In fact, when we go to create this, all we're going to do is focus on this little box right here, which is not part of the graph, but it helps us quickly sketch a good representation of this conic section. Though before I do any example, I want to just run through quickly the vertical oriented hyperbola, which will be exactly the same, except for where I have values for x, I'll have values for y, and vice versa. All right, for the vertically oriented hyperbola, we have exactly the same setup. We're just going to swap the x and y values. So instead of our vertices being along the x-axis here, our vertices are along the y-axis, and they have these very similar points. So this is 0, comma a. So instead of a, comma 0, it's 0a. And in this case, then we have 0, comma negative a. And then our foci are oriented along this transverse axis here. So out here, again, these foci aren't a part of the actual graph. They're a part of the construction of the graph. But we have two foci using this c value right here. So instead of c comma 0, we're at 0 comma c and 0 comma negative c. So those are the two foci. And finally, we have our slant asymptotes that run and help us with the construction of this hyperbola. We have one asymptote at y equals a over bx, and the second asymptote is y equals negative a over bx. All right, so that's like a fire hose of information at you. We're going to do an example now, a couple examples that should help ground you in the concept of what a hyperbola is. But important things I want to emphasize real fast that might have not been covered in enough depth when I was talking about it the first time. First of all, obviously, the positive term determines the orientation. If our x squared term is positive, we're oriented here along the x-axis. If our y squared term is positive, we're oriented along the y-axis. Second, in the construction of these hyperbola, when you're actually building them yourselves, you use this a and b value determined by these coefficients to build this little box right here. A will always be in these general discussions. A is always the coefficient related to the positive term. So A in this case is this width of this little box I've created along the x-axis. So it goes from A to negative A. And then from B to negative B, the values, the square root of those values, they're being divided by the y squared for the y. Exactly the same setup here. This goes for A along the y-axis up to A down to negative A, from B to negative B. I construct that box. Then what I do is I draw in these slant asymptotes. I can draw them in without ever knowing their equation because I have this box that helps me draw them in. And then from there, the actual sketching is pretty quick, pretty easy because I have this vertice and then I can draw this shape that acts asymptotically. All right, in this example here, we're being asked to sketch the graph of the hyperbola x squared over 16 minus y squared over 9 equals 1. We're being asked to also label the foci, vertices, and asymptotes. And I hope at the end of this example, you'll see that actually the construction of this graph is actually a heck of a lot easier than it seems when we were talking about the general form. First and foremost, I know that since the x squared term is positive, that the transverse axis here lies right along the x-axis, meaning my hyperbola shape is going to be oriented this way along the x-axis. My vertices are going to be on the x-axis right here. But beautifully, this is how I construct it. First, I was talking about that little asymptotic box. What I'm going to do is simply analyze, in this case, I have a squared equals 16, which means a equals 4. And here I have b squared equals 9, which means b equals 3. And in fact, just with that information, I can produce a rad sketch of this hyperbola. And what I do, so this a value is in terms of the x-axis. So along the x-axis right here, I'm going to go to 4 and 1, 2, 3, 4. And I start the creation. This defines the width of this asymptotic box. And along the y-axis, I go up and down 3. So up to 3 here, and then down to 3 here. And so all I do with this information, so again, 4 along, so I should label these right here. So this is at 4, negative 4 along the x-axis. This is 3, and then negative 3 along the y-axis. I'm creating this asymptotic box that I use to construct this. And actually, once I've created this box with this, I can sketch this graph. That's the rad simplicity of hyperbola. So first thing I want is I'm going to throw in these asymptotes. So I have asymptotes that run through the center here, through these boxes. So it will look like this is one asymptote. And then my second asymptote will look, stay straight, will look like that. I got a little bit wonky right there. Then I'm looking at this figure and I know it's oriented here along the x-axis. And if I refer back to that previous representation, I actually know where the vertices are. The vertices are where this little asymptotic box I've created intersects the transverse axis. So right here is that starting point. So these are the vertices, which I need to label here in a second. But my sketch of my graph comes directly after that. So I have asymptotic behavior, and then coming to these vertices, and then coming from this vertex, coming from that vertex, going to the asymptote. Same thing over here, vertex to the asymptote, vertex to the asymptote. And there, just with a quick analysis of these a and b values, knowing that the x squared term is the positive one, I've created a sketch of this hyperbola. Beautifully, when I create this sketch, just by looking at it and the general construction, I get these vertices really quick. And so in this case here, I have two vertices. and they're located at -4, 0 and 4, 0. And again, this number of 4 is related directly to this a squared value right here. And then I have these slant asymptotes. The slant asymptotes are defined by this rectangle, which helps me create this figure right here. But they're just y equals the rise over the run here. I'm going up 3 along the y-axis, and I have a run of 4. So the asymptotes are at y equals 3/4 x and y equals -3/4 x. So I've sketched a graph. I found the vertices. I found the asymptotes. The only thing I haven't do that was asked of me are find the foci. I do know the foci will be out here. Again, as with the ellipse, the foci aren't a part of the graph, but they help in the construction of the graph, and in applications they have a really important use. But in this case right here, what I'm going to use is the fact that c squared equals a squared plus b squared. And I'll plug in my a squared and b squared. That's a squared, that's b squared. So c squared equals 16 plus 9. Also work out nice. 16, or c squared equals 25. So c equals 5. So the foci always land on the transverse axis, which is determined by this positive term. So it lands along the x-axis in this shape right here. C equals 5. Well, this is telling me the x value, or the distance from the center the foci are. And so from the midpoint here, the origin, I'm going 5 units this way. So I get one foci that's right here at -5, 0. So this is a focus. And my second focus is over here at 5, 0. So again, just to review, the steps of creating a hyperbola are: 1, identify which term is positive. That will tell you if you're oriented along the x-axis or the y-axis. Then analyze these a and b values, which are the square roots of these coefficients, or what's being divided by each of these terms right here. Once you have your a and b value associated with the x term and the y term, you directly can create this asymptotic rectangle, or I like to call it a box right here. Then, once you've created this box, you actually can sketch the graph right away. You draw these asymptotes that go through the corners. You know that the vertices are where this rectangular box here intersects the transverse axis right here. And then all you gotta do is sketch a graph that goes towards those asymptotes. One thing important to mention at this point is some people think that these are like two parabolas, but parabolas actually don't act asymptotically at all. This is a similar but very different shape.